All right, hello everyone. Welcome back to Math 154, obviously. So this will be week 7, lecture 1. So we've only got 3 weeks left after today, essentially, and then a day of the final. So 3 more weeks worth of classes, day of the final, and then that'll be it. But let's not get that far ahead of ourselves. A whole bunch of my math lab homeworks due on the horizon since we've kind of had some clusters of sections completed all at once. We've had a few days in a row where we've completed 2 sections. So 4.1 and 4.2 due today. 4.3 and 4.4 are going to be due at the end of next class, this Thursday. And then 5.1 and 5.2 we will finish today, so they will be due on the 13th, which is a week from today. Remember, all due dates are 11:59 p.m. I was on the fence about whether I wanted to assign another Excel or discussion board or quiz or more than one of those things. I was really only thinking one because of the highlighted thing, but I'm just holding off. So do expect that you'll probably get at least an Excel and a quiz next time, if not one of all three. But for now, you do have one of each due today. So I'm giving you a little break since the midterm's coming up on those assignments. So just the 4.1 budget due today, that week 6 lecture 1 discussion board due today, and then the percent quiz also due today, remembering to pay attention to how we're answering that, following instructions, et cetera, as previously discussed. Another reminder that you are responsible for watching all recorded material. If you don't catch it all live, you go back and catch the YouTube replays, whether you just missed 5 minutes of it or the entire roughly hour and 50 minutes of it. I mentioned that because um, the view count I have for one of my videos where I had to do everything in advance, where I wasn't here that day, it doesn't even match the number of students I have, which means someone's not watching stuff. So that's all. I'm just trying to remind us that you are responsible for watching. If you think you haven't seen something, that's probably why, because I'm pretty meticulous in covering everything that should be seen. But the highlighted material, and if you checked your email, you should have received a poll that I promised was coming out that evening. And this was the poll, and the results were exactly as I expected, much more heavily leaning towards the Monday and Tuesday, the 12th and 13th, which was my intention to begin with, as I mentioned. I believe I had said that when I typed 11 and 12, I just wasn't, like I said, nobody's perfect. I wasn't paying attention. And then I was giving the introduction. I was like, wait a minute, that's a Sunday. Ooh, I don't know if I like that. So we are going to go with my original intention of the 12th and the 13th. I am sorry for maybe scrambling your brains by how I keep mentioning, a couple different dates. But this is definitively when you will take your midterm, the 12th or the 13th, whichever day is available to you. If you have to take it during our lecture, that's fine. Just make sure you catch the lecture on YouTube later. So 20 questions, 2 hours, only on chapters 1 through 4, nothing on chapter 5, nothing that we will be doing today, or the little bit of chapter 5 we covered last class. I've already talked about this in great detail, so I'm not going to go into much further detail. The test will be in my math lab. It will be the very top assignment on the 2 days it's available only. You only get one attempt. If you do not take the test, you will be required to have some type of documentation, some good reason as to why you missed it. If you just say, hey, I forgot, that's not an excuse. It's not going to fly. Make sure you show all your work. Make sure you number your problems. Make sure your name is on your work. Take pictures of it, scan it, whatever you have to do. Submit that in Canvas. You will see that location in Canvas. I believe I already have that available. I believe we've already talked about that. And remember that everything is due by 11:59 p.m. Remember that there is a review posted in Canvas that's about 55 questions. The formula sheet, which only has, I believe, 2 conversion formulas in it, is also in Canvas. So remember, anything having to do with interest formulas or calculating a weighted average, all those various mostly simple formulas that we've covered in this course, you are required to have memorized because they're more concepts than formulas, because they're all generally just 1 or maybe 2 steps. But I don't want to waste any more time with the introduction. Let's go ahead and get to the material. We are going to pick up where we left off, of course. We had given a very brief introduction with the concept of graphing lines. We had talked about how you only really need 2 points to form a line. However, doing 3 or 4 or 5 is nice because it confirms our suspicions. It confirms that everything fits the data. But when we're talking about application problems like we're about to do with our guided activity, of course, if they ask you to plot 5 or 6 or 7 points, then you have to plot the 5 or 6 or 7 points. So that's where we're going to pick up with our guided activity. Per usual, if you have any questions, I will be in the chat.
Humana, and this is going to be another one of those cases where I am going to use the slightly crummier handwriting on this thing because it would just be really difficult to do otherwise. So things will get erased as we go. So chapter 5 is all about linear functions, and 5.1 is called proportionality. I think I didn't say this, but chapter 5 is all about what we call lines. That's why the first thing we started talking about was lines. So we're introducing how proportions or how lines can sometimes be proportions and sometimes they're not. And again, when they're not proportions, they're still proportional-ish. They still change kind of like a proportion. It's just more like that temperature issue where 0 and 1 isn't necessarily 0 and the other. We talked about how all unit conversions are proportional with the exception of temperature because 0 degrees Celsius is not 0 degrees Fahrenheit. That statement right there very heavily ties into how lines are sometimes functions, are sometimes proportions and are sometimes not proportions. I saw this word function there, and that's what made me say it out loud. I didn't mean to say it. So ratios, proportionality, lines, all heavily tied together. And we're going to start studying this by talking about cell phone plans. And, you know, it's kind of an archaic cell phone plan, and these still do exist out there sometimes, but most of us have unlimited minutes at this point in our life. Most of us have unlimited text messages at this point, probably. All right, so this table is going to show the cost of monthly track phone plans as proportional to the number of minutes talked at rates of 5 cents and 7 cents per minute. So they're proportional, which means if you double the number of minutes you talk, then the cost you're going to pay is going to double as well. So what we're saying here is one plan, if you talk 1 minute, it costs you 5 cents. If you talk 2 minutes, it costs you 10 cents. If you talk 3 minutes, it costs you 15 cents, 4 minutes, 20 cents, etc. Versus another plan that 1 minute's going to cost you 7 cents. Second minute's going to bring you up to 14 cents. Talking 3 minutes is going to cost you 21 cents. Talking 4 minutes is going to cost you 28 cents, etc., etc., etc. Now, the first thing you're going to think is, well, why would you want the 7 cent per minute plan? Give me the 5 cent per minute plan. That's just silly to pay 2 cents more per minute. Well, we'll get into why you might take that one later. Spoilers, hidden fees. So from table 5.2, we created a graph, an XY scatter plot, coordinate pairs, rectangular coordinate system, Cartesian coordinate system, all that stuff's the same thing, which gives us a visual display of the relationship between the inputs and outputs, inputs being the number of minutes, outputs being the cents. Noting that the points for all functions all fall in the line starting at the origin. Now, this right here, starting at the origin, spoilers for later, but this is what makes them proportional. Because 0 and 1 is 0 in the other. 0 minutes means you pay 0 cents. So when your lines start at the origin, they're proportions. When they don't, they're not. That's the end-all be-all of whether lines are proportions or not. But even when they're not proportions, they're still proportion-ish. Which again, that whole rise and run thing is where that's going to come into play. And then we see a lot of things that I've already said out loud, so I'm going to go ahead and scroll down after I clear that. So here's our graph. So in blue, so the cool color blue is the nicer plan for now because we're paying less per minute. So 1 minute costs you 5 cents. So let's focus on the table for now. So 1 minute costs you 5 cents. 2 minutes costs you 10 cents. 3 minutes costs you 15 cents. So this right here, just looking at these two things, is the 5 cent plan. Looking at these two things is the 7 cent plan, so number of minutes and then the cost. I'm not a huge fan of how they set this up. I wish they would have done the more traditional way of just doing 2 tables of values. So for minutes and then cost, which is the 5 cent plan, we would just go 0, 0, 1 minute costs you 5 cents, 2 minutes, 10 cents, 3 minutes, 15 cents. And then you could have the other one, which I'm not changing the colors, the cost for the 7 cent plan. 0 costs 0, 1 costs 7, 2 costs 14, 3 costs 21. You get the idea. These are 2 independent tables of values, but it's still fine to do it this way. It's just when you have it this way, it looks more like an Excel issue where this is your input and these are your outputs based on the different costs. So 0, 0 was this point. 1, 5 is this point. 2, 10 is this point. 3, 15, right 3 up 15 is this point, and then you just connect them. Now, you saw me draw a line earlier that looked like this, where I put arrows on both ends. In this course, in this quantitative reasoning course, however, a lot of the times going into the negative region won't make sense. We can't talk a number of minutes, so it doesn't make sense to extend the line in this direction. So we don't. We can't talk negative minutes, so we don't draw that up. Now, what we could do is we could keep extending the line this way because this pattern will continue. It will continue forever and ever and ever, as long as it's not a complex model. And the same for the other one. So when we talk 0 minutes, we pay 0 cents, 1 minute, 7 cents, 2 minutes, 14 cents. Here's the 0, 0 still there. 1, 7, 2, 14. Now 14 isn't up here, so it's a little bit lower than the 15. And then 3, 21, that 21's a little higher, and the 7 was there as well. And that's how you get these points. You connect them, and the way I would prefer things are done outside of this little page right here is you extend it, because the pattern continues indefinitely. So that just looks a little better now with the arrows on the ends. Now, this right here, this right 1 and up 5, this is what I was talking about before with the consistent patterns. Every time we add 1 minute, this is going up 5 cents. Every time we add 1 minute, this is going up 5 cents. Every time we add 1 minute, this is going up 5 cents. Or for this column over here, every time we go up 1 minute, this goes up 7 cents, up 7 cents, up 7 cents. So if I gave you an equation for this, or if I asked you for an equation for this, you don't really need it to continue this pattern. You could just say, all right, well, if we go to 4 minutes, which is 1 more, we'd expect the 5-cent plan to go up 5 cents, which would be 20, and we'd expect the 7 cents per plan to go up 7 cents, which is 28. If we talked 5 minutes, which is another up 1, we'd expect this to go to 25, which is up 5, and we'd expect this to go up 7, which is 35. So this is a great way of finding patterns to extend your tables, which is what I had on those notes earlier. So every time we go right 1, that's the 1 minute increase, this goes up 5 cents. Or for the other plan, every time you go, let me put it up here, every time you go right, that's adding 1 minute. This one goes up instead 7 cents. And see, that's consistent. Spoilers, this relates to what we call slope, if I haven't already said that. Now, this problem was proportional, both of those, because 0 minutes was a 0 cost, so that makes them proportional. If 0 minutes cost you more than 0 cents or dollars, it would not be proportional, but again, it still just relates to it. And then the relation is this, as you see an increase in one way, the increase in the other way or decrease in the other way is consistent. So proportional means if you double one, you double the other, which means if you go up a certain amount in one, you go up a certain amount in another. That's the same idea as this, going up a certain amount, then go up a certain amount in the other. You just can't say if one doubles, the other doubles. That's the only difference there. All right. So let's take this problem that we just did. We're going to go higher on the minutes. We're not just going to talk a couple minutes. We're going to talk hundreds of minutes. And now what we're going to do is we're just going to talk about the 5-cent plan, and we're going to input a hidden fee, so to speak. So now we've got a $20 fixed cost as part of this problem, so it's a lot more realistic to a true cell phone plan. Most plans aren't just pay by the minute. They're, all right, if you don't talk at all, you're still going to pay 30 or 40 bucks. If you talk forever, you're probably going to pay 35 or 40 bucks maybe, I guess. But we're going to do it based on these numbers. So cost is proportional to minutes you speak at a rate of 5 cents per minute. Again, that is what we saw earlier. This is nothing new. Cost is proportional, which means if you double one, you double the other. But now we're also going to assume that on top of that, there's an additional fixed cost of $20 each month. So that's our taxes, our fees, etc. So what we have here is, I'm going to go ahead and get the graph up here. If you ignore this, that's what we were just doing before, but now in hundreds of minutes. So our cost is now in dollars. So 100 minutes would be 500 cents, which is $5. 200 minutes, $10. 300 minutes, $15. 400 minutes, $20. We're only talking about the 5-cent plan, not the 7-cent plan. But again, this is not the true cost. Your true cost is over here. That was weird. Undo, please. Thank you. This is the true cost with everything accounted for. So you had what we call the variable cost, which was your minutes, but then you have your fixed cost, which doesn't depend on how many minutes you talk. So that's this just extra $20 you slap on the bill no matter what. So if you pay $0, that's what the dash means, $0 in your minutes, you still pay $20 for the fee. If you talk for 100 minutes, you pay $5 for your minutes, but you still pay that extra $20 for the fee, bringing your total cost up to $25. If you talk 200 minutes, your minutes cost is $10, add in your fixed fees, and you got a $30 cost, et cetera, et cetera, et cetera. Now, it's still pretty easy just to, all right, well, this went up 5, this went up 5, this went up 5, every time this went up 100, every time this went up 100, every time this went up 100. The same is actually true over here. This still just goes up 5, this still goes up 5, this still goes up 5. Now, it doesn't go up 5 from these numbers, it takes these numbers and adds 20. So just to go from here to here, you're adding 22. Again, that's your fixed cost. A fixed cost is just added at the end. So we have two types of cost here, which will be laid out on the notes in a few minutes. A variable cost and a fixed cost. And the words variable and fixed mean they change or they don't change. Just kind of like when we fix Excel references, we say that it's not that they were broken and we unbroke them. It's they're rigid, they don't change. So that's what we mean by fixed, it doesn't change. This is kind of like your rent. Your rent doesn't change every month. Your electric bill might change, your water bill might change, but the actual rent does not change until the next year maybe. But then you can just make a new model after that. This is a very important concept. This is going to be seen all chapter long, and the concept will go into the real world with you. A lot of things in the real world are just based on a sum of a fixed cost and a variable cost. The word variable means change. Fixed means it doesn't change. All right, so what's all this stuff down here? And again, you could say, all right, 600 minutes without the fee would cost you $30, fee accounted for 50, and you could keep going. And they only plot the first 4 points. They don't do the 400 and the 500 just because they were going to run out of room, I guess. So the red one is just the 5-cent plan without the fixed costs accounted for. So because this one starts at the origin, this one right here is proportional. I really don't want that color though, since it's red. So this one is proportional because it starts at the origin. This one does not start at the origin, so it's not proportional. Again, it still has the idea of being proportional, that as you increase one a certain amount, the other increases a certain amount, or even decreases a certain amount. So the red one was these, sorry for the wrong color, but that was the red one. So here's your 0, 0. 100 minutes is $5, 200 minutes is $10, 300 minutes is $15. Now these black vertical lines, this is not something you are traditionally going to draw. These black lines are just demonstrating the fixed costs. It demonstrates what the fixed costs does. It just shows that the fixed cost takes this line and it bumps it up $20. That's all that's showing. Because this one is $20 higher than that one. This one is $20 higher. This one is $20 higher. This one is $20 higher. That's all a fixed cost does, or fixed whatever. It doesn't have to be a cost. it just shifts things up. So again, these little black vertical arrows, this is not something you would traditionally draw in your homework, on a quiz, on a test. In Excel, you won't see them. I'm not going to ask for them. It's just a demonstration here. So don't get used to that. Right. So now that we've seen an example, let's try out one. Let's see if we can actually do this on our own. Can I zoom in? That's too far. That is just right, it looks like. All right, I'll scroll down a little bit in just a minute to that. So weight of water. The weight of water is proportional to the volume at a rate of 8 pounds per gallon. So when we say something's proportional, it just means that you can have that multiplier. You have like a y equals kx kind of setup. But then we're going to assume that we're not just going to be measuring the weight of water, we're going to have a bucket to put that water in. And we've got a really heavy bucket. This thing's made of solid steel, and it's 10 pounds. So we want to do some what if analysis. What if we put a half a gallon of water in? What if we put a 1 gallon in? How much does the water weigh, and how much does everything weigh? So this is just the water, and then this would be with the weight of the bucket as well. So we said that weight of water is proportional to the volume at a rate of 8 pounds per gallon. 8 pounds per gallon. So that means 1 gallon weighs 8 pounds. 2 gallons would weigh 16 pounds, et cetera, et cetera, et cetera. Not the other way around. It's not 1 pound is 8 gallons. You have to make sure you're getting that right, which I can no longer see on my screen. So 3 gallons, 24 pounds, et cetera, et cetera, et cetera. And you could even do a y equals 8 times x kind of setup, where x is your number of gallons, and y would be your weight. That's something that we'll get into a little more directly later, but I wanted to go ahead and give you the idea. But that's only dealing with this one. It doesn't include the 10-pound bucket, because with the 10-pound bucket, with that fixed amount that just always adds 10 no matter what, that's a fixed amount, which doesn't make it proportional anymore. It just means you take the proportional part, you take the proportional part and you just add 10. It's very self-descriptive. All right, so if you have 0 gallons of water, clearly it's 0 pounds of water. If you have a half a gallon of water, well, if 1 gallon is 8 pounds, so if you double one, you double the other. That also means if you half one, you can half the other. So half of a gallon would be half of 8 pounds, which would be 4 pounds. You could also just throw in 0.5 into this. 0.5 times 8 is 4. 1 gallon would weigh 8 pounds. 1.5 would weigh 12. And instead of keep doing math by plugging it in here or trying to think things out this way, I could just say, oh, well, every time we go up 0.5 gallons, the weight goes up 4 pounds. This is up 0.5 gallons, and this was up 4 pounds. So the next one, if we go to 2 gallons, this should be 16. If we go to 2.5, this should be 20. Every time I go up a half, I'll go to 24, 28, 32, 36. That's the pattern in a larger table. But then what we do is we want to find the total weight, because we can't just put a half a gallon of water onto a scale. You have to put it inside of something. And we found ourselves a ridiculously heavy steel bucket that weighs 10 pounds. It's exactly 10 pounds. So we just take the water weight and we add 10 pounds to it. So if there's no water, that means it's 10 pounds with the bucket. If there's 4 pounds of water in there, it's 14 pounds in the bucket included. If you have 8 pounds of water, that's 18 pounds including the bucket. 12 pounds of water would be 22 with the bucket. 16 pounds of water would be 26 with the bucket. 20 pounds of water would be 30 pounds with the bucket. Now again, the change in this red every time, it just goes up 4, up 4, up 4. But to go between the blue and the red, you're adding 10 because that's what the bucket's fixed weight was. The water is a variable weight because we're allowing ourselves to put different amounts of water in. We're not having different weights of buckets. Now I might say, well, Mr. Beckner, why don't you just put the bucket on the scale and hit tare? And I go, yes, absolutely, that's what you do in real life. But the point is, when you've got to pick this bucket up and carry it somewhere else, you're going to be holding that 10 pounds of the bucket in addition to the water. So let's go and graph these with appropriate colors. So we'll do blue for the no bucket. We're just weighing out the water. So this is what we might see on the scale if we were to hit tare. And they even plot the first ones for you kind of nicely, but that's all right. We don't have to do it. We still do, 0, 0, that's the origin. Now 0.5 gallons is 4 pounds. So we go right a half and we go up 4. These graphs are also done very nicely for you, as you will see for the blue pattern coming up. 1 gallon of water weighs 8 pounds. 1.5 gallons of water weighed 12 pounds. 2 gallons of water weighed 16 pounds. 2.5 gallons of water weighed 20 pounds. 3 gallons of water weighed 24 pounds. And this is what I mean by they're nice. All of those are on the little corners of these grids that you see, but only for the blue. It's only for the part that's proportional, not including the bucket. And then all you do is just connect and extend. I'm going to do my best to make this as straight as possible. Please do not judge me. I am on a blind tablet, nor are my artistic abilities that great to begin with. That's pretty good. Now again, me personally, I would want a graph big enough to continue this pattern and show that it goes on forever and ever and ever, or at least for quite some time. So that was no bucket. Now let's do in red with the bucket. So this is what we would have seen on the scale, but when we go to pick it up and haul it somewhere, we're really going to feel the red curve. So 0 gallons actually weighs 10 pounds because we got that bucket. Now there is no 10 directly on it, but 10's halfway between 8 and 12, and that's going to be consistent. 14 pounds with the bucket when we had a half a gallon of water. So that's going to be here about halfway between 12 and 16. Then 1 gallon of water in addition to the 10 pounds of bucket was 18 pounds. 1.5 gallons of water plus the bucket was 22 pounds. 2 gallons of water plus the bucket was 26 pounds. 2.5 ends up being, I drew up 3. That's what was throwing me off. I went too far. Then 2.5 was the 30. Yes, 30. There we go. Draw. Where's my eraser? There we go. So I just shouldn't have had that point there is all. That's not a big deal. It's not wrong. I just could have done my arrow right here instead, and I'm still on the grid, which is perfect. So that's still the no bucket. Now we go back to red. I don't have the extra point plotted. It would have been off the grid. Nice straight line, doing our best. Sorry for any little perturbations. And then keep going just to show the pattern, and that's with the bucket. Now again, excluding the bucket, this is a proportional problem because it went through the origin with no bucket, but with the bucket's weight, with that fixed weight in addition, this is no longer proportional. It still has that nice relationship that every time you add a half a pound, the weight goes up 4 pounds, and that's true every time you go between points. So you could find the next one that way, 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 without having to get to the fact that this equation is y equals ax plus b, and knowing what the a and b are, plugging it in and doing algebra and arithmetic. You can just follow a pattern. Patterns are amazing. They can get jobs done quicker most of the time. Now, they do ask for the axis labels down here. We don't want to miss that. The axis label, the horizontal one, was going up in gallons. And then this vertical one was our weight. Now, I said gallons here and weight here technically. Technically, some teachers might not like that because one is a units and one is an actual type of thing. So the gallons would be a volume, and the weight would be in pounds. So you could put gallons versus pounds, you could put volume versus weight. You could mix them up, and I would not care, but some teachers might. All right, so let's clear the screen, and let's do another. How are we on time? 15 minutes. Of course, this one is on 2 different pages, so I'm going to have to scale back quite a bit. The cost, I'm covered, the cost is proportional to the number of tickets you buy at a fair at a rate of $2 per ticket. So maybe it's 3 tickets for one ride, 1 ticket for another ride. We don't need to know all that stuff. We just know it's $2 per ticket. But in addition to that, there's a fixed cost of $15 just to get into the fair. Now you might say, that's pretty unusual. Most of the time you can just walk in and there's no fee. Well, drive to Busch Gardens and tell me that you didn't just pay 15, 20, 30 bucks for parking, which would be a fixed cost. Now, if you have 4 or 5 people in the car, you can divide out that fixed cost, but it's still a fixed cost. And then you have to pay for your tickets when you get in, which would be your variable cost based on the number of people. All right, so $2 to get a ticket for each ride, $15 just to get in. Maybe they've got shows and stuff happening to make it worth that 15 bucks. I don't know, not the point of the problem. The point is, no matter what, you're paying 15 bucks whether you ride any rides or not. If you want to ride some rides, you're paying $2 a ticket, and then, let's just say it's a ticket for every ride. Just keep it simple, not that it matters at all. So fill in the table of value. So this is just the number of tickets. Let's go back to blue. Blue, please, thank you. So this is just the cost for your tickets. This is your total cost. So if you buy 0 tickets, you're not going to pay any money for tickets. If you buy 5 tickets, they cost $2 each. So the first one costs you 2, the second one 2, 2, 2, 2. That would be $10. 2 tickets per at $5. I'm sorry, $2 per ticket, and we're getting 5 tickets. 2 times 5 is 10. So every time we go up 5 in the tickets, the cost is going up 10. So this went up 5, which means the next one will be 20. You don't even have to think about it any past that. This goes up 5, so this will be 30. That's 10 more. Then that goes up 5, so this will be 10 more, 40. This goes up 5, so this will be 10 more, 50. It's just a quicker way to do things when you've got these patterns. Knuckles popping if you hear that. Sorry if that bothers you. But the total cost, we don't just buy tickets, we have to pay that $15 gate fee, that fixed amount. We don't pay $15 for ride 1 and then $15 for ride 2. We just pay the $15 once. So even if we pay $0 for our tickets, we still pay $15 to get in the gate. If we pay $10 for tickets, we got to also pay the $15 to get in the gate. 10 plus 15 is 25. If we paid $20 for tickets plus the 15 to get in the gate, that's 35. Now look, each time this is still going up 10, so I don't have to keep thinking about it that way. I can just keep adding 10. 45, 55, 65, boom, done a lot quicker. You could also say the main idea I was going with originally was this cost in comparison to this cost. To go from here to here, you're just adding 15, and that's because of the fixed cost saying just add 15 to the variable cost. Now let's plot some points. And I meant to switch my color there. Dang it. 15, I'm going to erase it. It's going to get too ugly otherwise. Draw, so 15, 25, 35, 45, 55, 55, 65. That's a 55 there. All right, so in blue, we got the origin. 5 tickets cost us 10 bucks. 10 tickets cost us 20 bucks. 15 costs us 30. 20 would cost us 40. And then 25 would cost us 50, and that's where we stop. But I could keep going and say that 30 would cost us 60, 35, 70, 40, 80. It just keeps going forever and ever and ever and ever and ever. Because this is a simple model. Notice I just said because this is a simple model. So this was no fee, no gate fee. But then we have the 0 tickets still cost you $15 in reality to get in, maybe go see some shows and stuff. Then if you buy 5 tickets, in addition to the $15 gate fee, it was 25. Then it was 35 for 10, 45 for 15, 55 and 65 for 20 and 25 respectively. Connect, extend, and that was your total cost with your fee included. And again, I'm not doing what that original problem did. I'm not showing these little, oh, that's just demonstrating that the fixed cost adds 15 each time. That's all that's doing. Again, that is not a traditional thing that we would show, which is why I'm erasing it now. I'm just trying to give you something in relation to the first one you saw. For the axis labels, the 0, 5, 10, 15, and 20, etc., that was the number of tickets. And then this axis, the vertical one, these were costs. You could put in dollars if you like. These labels, I can't tell you how many graphs and charts I see in the media that don't have labels on them. You know why? Because they want to confuse you. They want to mislead you. Labels are critical. All right, let's do another one. Here we go. Driving distance. The distance you drive is proportional to the time driving at a constant speed of 40 miles per hour. This is true. No stoplights, no turns, no potty breaks. If you just get on the road and you're going 40 miles an hour and you're driving through the desert of Nevada trying to go count some ballots, sorry, relevant, nothing is going to prevent you from, hold on, let me see that. Nothing is going to prevent you from maintaining your speed. You can just keep going 40 miles an hour for several hours and nothing's going to stop you if you didn't drink a bunch of water or whatever. So that's what we're going with here. The distance you drive is proportional to the time driving at a constant speed of 40 miles an hour. But let's say when you were on your drive in the desert, assume that you already drove 100 miles before you started keeping track of everything. So let's say you filled up your gas at a gas station, your gas tank at a gas station. You start driving 100 miles into the desert and you realize, oh shoot, I forgot to reset my trip meter, the thing that keeps track of how many miles you've got on your tank of gas currently. You have your odometer and your tripometer. So you reset it and you go, well, shoot, I drove 100 miles. Now I'm missing that 100 miles in my trip. And if I know maybe I can go 400 miles before I run out of gas, that means when I see 300 on my trip, I know I'm going to be out of gas because of that 100 miles already there. That's kind of what we're getting into here. All right, so excluding your trip reset 100 miles already driven, if you drive for 0 hours, you will have gone 0 miles. If you drive for 1 hour, well, you drive 40 miles per hour per 1 hour, so 1 hour is 40 miles. So when our time goes up 1 hour, our distance goes up 40 miles. So when we go up another hour, we expect to go up another 40 miles and we'll be at 80 miles. Also, 2 times 40 is 80. 3 times 40 is 120, and guess what? When you go up 1, you go up 40, boom, 120. Then 160 because we'll go up another 40, and 200 because we go up another 40. Now, you knew that the 40 was going to be a multiplier, but if you do it backwards, if you took your distance and multiplied it by 40 and you thought that was time, you'd get some answers that wouldn't make sense. For example, if you think, all right, if I go 1 mile, how long is that going to take? If you took 1 times 40, that would tell you that 1 mile takes 40 hours? Wait, what? 1 mile takes 40 hours of time? No, that would not make sense. Clearly, you've done something wrong. Remember, we are asking ourselves if things make sense. We are establishing critical points. All right. So it seems like 5 hours in, we've gone 200 miles. But again, this time is just from us hitting the reset button on our trip where we had already gone 100 miles. So this is an addition to the time on the trip and the distance on the trip. So while when we hit reset on the trip, it now says 0 miles, in reality, we've gone 100 miles. We've already got that on the clock. That's the fixed amount that was already on the clock, already on the trip before we hit reset. Now when our trip reads 40, that means we've really gone 140 miles. When it reads 80, we've really gone 180 miles. When it reads 120, 3 hours into hitting reset on the trip, we've really gone 220 miles. Then 260, then 300 as you keep just adding 40 over and over and over. That addition is consistent between these two values. It's to go from one to the other. That's when we add the 100 to go from blue to red, blue to red, blue to red. That's just the fixed amount. And maybe there's another reason why we reset the trip. Maybe there's another reason we have this 100 miles factored in that we already drove. But you get the idea. So let's plot them. All right, I gotta be a little quick. 0, 0, 1 mile, 40, 1 hour, 40 miles, 2 hours, 80 miles, 3 hours, 120, 4 hours, 160, 5, 200. This was not including the 100 miles we already drove, and we continue the pattern. So excludes the 100 miles driven initially. Then in red, what we're going to notice is we're just going to take this blue thing and we're going to lift it up exactly what that extra mileage was, that extra 100 miles. So that's a height of 100, then 140, 180, 220, 260, 300. Continue on, and that's the total distance driven. Now, as we move on through the sections, we're only going to be interested in the red one. We would not care about this blue one at all. We don't want to make two different graphs on the same thing. We would only do the entire model, not just part of the model. So again, in the future and in your homework, we're generally not doing just part of it. You would account for everything. Now, maybe there was no fixed 100. If that 100 was not there, then the red curve wouldn't be there at all, and your answer would just be the blue one. And again, in your homework, typically you're only doing 2 points because all you need is 2 points to form a line. I can remove all but any 2 of these points on the red one and it'll stay the same. Any of the 2 points on the blue one and it would stay the same. All right. Clear our screen, come off of annotate. We got like 2 minutes left. I want to show you the next little bit, and then we'll call it a day. This is what I've been talking about quite a bit. We just didn't have it written down. Linear equation. So the equation that would make that picture that's a line can be expressed, words are hard. Linear equations can be expressed as some total amount is the variable amount plus a fixed amount. Let me put that on the same line. It's a variable amount, which was us taking the number of minutes times 5 cents per minute, then plus the fixed amount, which was us adding the $20 flat fee every month. So this variable amount is the part that changes, and in order to change, you're going to have to multiply it by a variable. I've been saying that y equals kx setup was kind of similar. In fact, it's exactly the same for that. You just take your 5 cents per minute and you multiply it by your number of minutes. But we don't know what the number of minutes is for every scenario. That's why we call it x, or m for minutes, or whatever letter you like. So when we come back next time, we're going to go back to those 3 or 4 examples, and we're going to write up equations, something like y equals 3x plus 5, where the 3x, this would be your variable amount, and the 5 would be your fixed amount. So this 3 is always the amount per blah, blah, blah. So the cost per minute, or the weight per gallon, or the driving distance per hour. So that number is always the thing that has a per in it. The fixed amount is always the number that doesn't have a per in it. It's the thing that you're just adding one single time no matter what. So that adding $20 to the cost per minute value. So this 3x plus 5 or 2x minus 7, this is going to be pretty consistent with what we see with these variable amounts and fixed amounts.
All right, sorry about that weird pause, just getting the next part set up. Here we go.
To finish all of these notes, we had just talked about how linear equations can be expressed as a total amount being the sum of a variable amount, which means an amount that changes. That's what the word variable means. It varies. And a fixed amount, which is an amount that doesn't change. So if you wanted to break down, the amount it costs for you to live in your home each month in a very simple way, you could say you have the rent portion or mortgage portion, which is typically a fixed amount that doesn't change from year to year. Well, rent might go up every year, but your mortgage wouldn't. And then you have your variable amount, which would be things like your electric bill, your water bill, that would depend on how much electricity you used or how much water you used. Now, in the real world here, electricity and water, they're not a linear rate, unfortunately, but they can be approximated as one. But that's something that we're going to get into over the next several chapters, how a mathematical model will be good for one amount of time or one kind of range of values, but eventually it kind of falls apart. And that's not true of all models, but when we try and model things like population size, any financial dynamics, eventually these models kind of fall apart. The same can be said of trying to model a population with a disease count. That might be relevant to right now. A lot of people will say, oh, well, it's exponential growth. And that is true for a short period of time, but eventually it becomes something known as logistical growth, which we won't actually study in here. And that's because there's a ceiling as to how many people can get sick. Anyways, I'm rambling. Let's get back to these simple concepts. We're starting at the basics. Total amount is a variable amount plus a fixed amount, which we said the variable amount has to have a variable. So it's usually something like total equals 5x plus 3. I think I gave similar numbers last time, maybe 3x plus 5, where 3 would be your fixed amount. So that's like your mortgage. And then 5, that's saying that for every single x, you're paying 5 of something. So if x is 1, you're paying $5 or cents for the first one. If you have x is 2, you'd be paying 10. If x was 3, you'd be paying 15. So this is the variable amount. And when you're dealing with real world context, the variable amount usually has the word per in it. So the variable amount usually has the word per. So it'd be like $5 per ticket. So it's not saying you just pay $5 no matter what. It's based on the number of tickets. It's an independent-dependent relationship. So what we want to do is we want to take this idea of being able to write equations for our models, and we're going to go back to the 3 or 4 problems we did last time where we graphed them, and now we're going to actually write out their equations. And you can use words, you can use letters, you can always use y and x if you really like, but I'm going to try and stick to letters that are a little more relevant for the problem. So again, what I'm referring to is we made these 3 graphs. We did a graph for the weight of water based on with the bucket and without the bucket in that opposite order. We did buying tickets at a fair or Busch Gardens or something where we had the $15 flat fee to get in and then $2 per ticket. So we had a graph without the flat fee and then with. And then the same thing for a driving distance. So if you have not seen that yet, that means you need to go and watch last class's lecture. So this is what we're getting to now. Zoom in just a little bit. There we go. So blah, 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 blah. Constant of proportionality is a rate. That's something that we have discussed before. A constant of proportionality is a rate. This is back when we were talking about that y equals kx stuff. K was the constant of proportionality. And that was always, it would always have a per in it. So 5 per 1, $5 per 1 ticket, something like that. So going back to the previous problems, the cell phone problem in particular is what we're looking at here, where we had 2 cases. We said, all right, one plan was 5 cents per minute, another plan was 7 cents per minute. So we could say the cost in cents for the first one is 5 times the number of minutes, which we could use the letter M to clearly represent minutes. Or for the 7 cents per minute plan, that cost would be 7 cents per minute. But this was not the total cost. That was just the proportional part. That was the part without the fixed amount. So again, the fixed amount, this adding of a number, makes something no longer proportional. It still has some similarities, which we talked about being the slope, which we'll talk about in more detail in 5.2. but it doesn't go through the origin anymore. You can't just say as one doubles, the other doubles. It doesn't quite work the same. So what's going on with that 20? Well, that's when we took the $20 monthly fee. Now we're only doing this one, at least for now. Yeah, no, we're only doing this one with the 5 cents per minute plan. So we're not going to do the 7 cents per minute plan with the full cost, including that hidden fee, which is not technically hidden. We're seeing it right in front of our face. So this 0.05 M is the same thing as this, except now our cost is in dollars. These two things are the same. It's just one is in cents and the other is in dollars. But then this is a total cost. So we're adding in that fixed fee, that flat fee we pay every month of the $20. So this 0.05 M, that's our variable amount, and then the 20 is our fixed amount. And as always, our variable amount needs a variable next to it. So this is our goal for the next three problems. We want to be able to write something like this or like this. Now, they say this is not proportional, again, because of the 20. We've already discussed that. It's similar but not the same. This model uses C and M, so things are very clearly labeled. Also, this is a perfectly fine model, or directly above it, it uses words. Now, in my math lab, if you're typing in the model, they're probably going to want you to just use the letters. But then you have a third version of it down here with, instead of C and M, Y and X. So this is perfectly fine, but unfortunately, what you would need to do is really write down that X is the number of minutes and Y is the cost in dollars. If you just write it this way, your variables are not labeled, you don't know exactly what it relates to, it's not very clear. At least by using C and M, there are hints as to what they are, but I would still love it if someone didn't write all of this part, if someone wrote somewhere that this C is the cost in dollars and that M was the minutes. I know it feels less necessary, but you never know what'll happen when you want to look at your notes a year from now or 2 years from now, and all you see is C equals 0.05 M plus 20, and you go, well, what the heck was M? What was C? I don't even know. All right, so I got to clear my screen. Let's go off of annotate. So we already did the first one. Don't worry about this little sub 2. We're not going to do any of that. I don't even know why that's there, but it's okay. If they were going to call that 2, they should have called this a 1. That's all I mean. So for problems 2, 3, and 4, this is our goal, 2 parts, A and B. 1, we're only going to write the proportional part, which is only the variable amount. So this is not including the fixed amount. The cost is the 5 cents times the number of minutes. But then for part B, we add in the fixed amount for whatever the problem was. So that's what we'll be doing for questions 2, 3, and 4. Can I get all these on the screen at once? Perfect. All right. The weight of water is proportional to the volume at a rate of 8 pounds per gallon. Write an equation for this proportional relationship. We're ignoring the bucket. The bucket doesn't exist. We're only worrying about the weight of the water. 8 pounds per gallon. So the weight is proportional to blah, 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 blah. So that says we should write something like weight equals. So the weight of the water is means equals, and then proportional, that's where you have your y, your kx, or whatever number and letter or word you want to use. But the rate is 8 pounds per gallon. So for every 1 gallon, you would have 8 pounds of weight. So that 8 is the k. This 8 is the k. Now, maybe it's 1/8. If you had this solved for the the volume instead, it would be 1/8, but that's why I said to make sure we're doing this in an appropriate way. And you can always check this at the end. You can plug in some numbers and see if everything makes sense. So 8 times, so that's weight equals 8 times the gallons. Gallons is a type of volume. If you wrote weight equals 8 times gallons, that's okay, but I might prefer something like pounds equals 8 times gallons. Because then they're both talking about units and not one is a label and the other is units. Or you could just go W equals 8V, as long as you establish somewhere that W is weight and V is volume. So what you can do is you can use this equation and go back to that table before, and I'm not going to be able to do that because I'd have to erase everything and move, and it's just time consuming. That table, we had something like 0, 0.5 is 4, 1 is 8, 1.5 is 12, and you could plug in any of these volumes and you should get the weight. So if you plugged in a half, 8 times a half is 4, and you get the right thing. If you plug in 1, 8 times 1 is 8, and you get the right answer. If you plug in 1.5, 1.5 times 8 is 12, and you get the right answer. It works. Part B, now we're going to assume that we have that bucket. So we're talking about the weight we're actually holding. And that bucket weighs 10 pounds. So we said all we do is just have this be the fixed amount, and we add it to the variable amount. So now our weight is 8V, there's the variable amount based on the water itself, and then we add the bucket, which is always 10 pounds no matter what. See, the bucket doesn't change weights, it's the water that changes weight. Or if you prefer, weight equals 8 times volume plus 10. Again, use your words, use your letters, whichever you're more comfortable with on your own. My math lab, you're probably going to need to use letters. They may tell you to use Y and X. They may not. You just have to pay attention. All right. Next up, let's make the next equation. Sorry about that. The cost is proportional to the number of tickets you buy at the fair at a rate of $2 per ticket. So the cost is blah, 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 blah. So we go cost equals, and it's proportional. So the next thing is just going to be a number times a variable. And the number is, I think, very clearly the $2 per ticket. That's the per, so that's the thing that goes in front of your variable. And then per ticket, so 2 times the number of tickets. It doesn't say 2 tickets, it says 2 times the number of tickets. Or you could just go C equals 2T, or you could go Y equals 2X, but you have to write what X and Y are in that last one. If you want to use Y and X, you absolutely need to label them. Otherwise, I'm going to go, well, which is which? You didn't tell me. Now, when we account for the fact that we had that $15 flat fee to get in, but that's fixed, so that's not going to be multiplied by anything. This does not depend on some other amount. So now it's cost equals 2 times the number of tickets. I don't know why I just did it. That, there we go. And then plus the 15. That's all it is. Or C equals 2T plus 15. It's nothing super crazy, but as always, if you don't practice it first, you're not going to know what to do. You need to see it executed. You need to try it yourself. You need to practice it 3, 4, 20 times until you get used to it. It's just like anything in life. You're not going to be amazing at it the first try in general. Some people will get lucky and they are. Most of us have to practice things. All right. Finally, that driving distance. So the distance you drive is proportional to the time driving at a constant speed of 40 miles per hour. Now, honestly, you don't have to be told everything so blatantly mathematically. You don't have to, the distance you drive is proportional to the time driving. Someone could just say you're driving 40 miles an hour, and that's implying that your speed isn't changing. 40 miles per hour, that word per is a massive clue that it's a proportional relationship. Again, just that part, not accounting for the 100 extra miles, just in this parameter only. Per is a clue that that's a y equals kx kind of setup. So you go, okay, well, we're talking about distance and time. We usually are much more interested in going distance equals, I'm saying usually, but not always. And the phrasing of this does imply that we want to go distance equals blah, 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 blah. All right, well, 40 is our multiplier, 40 miles per hour. And then you could go times time again, if you like here. And if you don't trust this, if you think maybe it was supposed to be time equals distance times 40, then plug a number in and see if it makes sense. So plug in 1. If you go 1 hour, would it make sense that you go 40 miles? If you go 40 times 1, you get 40 miles. Well, yes, because your speed is 40 miles per hour. So 1 hour should get you 40 miles. And again, the abbreviated version, D equals 40T, would also work. Then we assume that we have that 100 miles we already drove. That's not going to be affected by our speed at all. That's a fixed amount. So we just go d equals 40t plus 100, or distance equals 40 times time plus 100. And again, you can always label things in terms of units. You could write that t is in hours and d is in miles. But that would also be true with different units as well, but you just have to be careful in how you make your assumptions. But again, I think a lot of people might want to actually label their units. That was weird. I hit mute for a second to cough, and then I couldn't unmute it because of my annotate. All right. Always something. Clear. Off. All right, there we go. Now, I am going to do another one of my reminders. Also, I'm basically letting you know what the next Excel file is with this, that almost every Excel file from this course has a little preview in your guided worksheets. I know we've talked about this before, but I know a lot of people need reminders of stuff too, with so many different things going on in this class. So here's a picture that might help you know whether you got your graph right or wrong when you go to do this assignment, because a lot of people end up having an extra line in this or one less line than what's necessary. So you've got something to compare and contrast to. So just remember that. So yeah, FYI, this is going to be our next Excel homework 4.1 lines. But I'm not giving you a due date yet because I want you focusing on the test, the midterm. All right, so that's that for that. 5.2. Slopes and y-intercept. So you've already heard me say that word slope many times already. We talked about that rise and run concept, but we're just gonna lay it out in full detail now. So slope is the measure of the steepness of a line. Slope is the measure of the steepness of a line. So if you have, here's a line over here, let's put our axes. Let's say we got a point at this height right here, and then the line just kind of keeps going up from there. And let's just pretend like this number here is 12. And then as you move along this line, you're going right and then up, right and then up, right and then up, right and then up. Let's say you're going to go right 5 and then up 1. You'll go right 5 and then up 1 again to get to another point. Then you can go right 5 and up 1 to get to another point, et cetera, et cetera, et cetera. The 5 in this scenario is what we would call the run, and the 1 in this scenario is what we would call the rise. Rise is how far up or down you go. Run is how far right you go. There is no left. There is no left. There is no left. Say it with me. There is no left. There is only right, up, and down. We are only ever going to be considering ourselves moving right with these problems. We're talking about slope. Slope is rise over run. Slope is a rate. Slope is a rate. It's a rate of change, in fact. The word rate. I feel like we've heard that at least once in this class, right? You're darn right we have. Rate means ratio. It means fraction. And look at this. This formula has got a fraction in it. So slope is a rate. It's a fraction of something. Something on top of something. Well, what are the tops and bottoms? It's a rate of change. Change, as we were talking about in the last 2 sections of chapter 4, well, there was 2 types of change. We had total change and percent change. But if you don't throw the word percent in there, change is assumed to be a difference. Change is a subtraction. It's specifically new minus old. So if you have 2 points on a line, x1 comma y1 and x2 comma y2, your slope is calculated by the change in the height. So the change in the y values, how far up or down you go. So these are your y values. So that's your top. And then 2 minus 1 would be new minus old. And then the change of the x values would be the difference of these. And again, new minus old, the second minus the first, and that's this. A lot of people like to say, oh man, the slope formula, that's a pain to memorize because it's got these little numbers in there, it's a fraction, it's subtractions. What order do I do things? Do I do the x's on top, the y's on top? I don't know. Remember that slope is the rate of change. Remember, I try and suggest to not just memorize blatant formulas, but concepts. The concept here is that slope is a rate of change. Rate means fraction, change means subtraction. So we're going to have subtractions in the top and bottom. What is the rate of change specifically? It's rise over run. Rise implies height. Height is y values. Run is how far we go right. Right is x values. So it's supposed to be the vertical change divided by the horizontal change, which is why we go y2 minus y1 over x2 minus x1. I don't care how you memorize that formula, but you have got to memorize that formula. We are going to be using that over and over and over and over and over. If you blatantly memorize it like an algebra student, that's fine. If you understand the concept and the definition of slope and what it truly means, that's the quantitative student approach. Rate of change, rise over run. Pairing those things together spits out the formula instantly. Now, there is another definition up here that I did not talk about immediately, but that's for a reason. The y-intercept. This is going to be very true in this course. Can be. And it's not always going to make sense. Your y-intercept can often be interpreted as a starting value or a fixed value. Those are interchangeable concepts. So you might think about what do we have at time 0 when nothing happens? Or what do we have when we talk no minutes? What's that flat fee we pay, that $20 that we pay for the 5 cents a minute plan? So a y-intercept can be interpreted as a starting value or a fixed value, one or the other. It just depends on the concept, whether you want to consider it as a fixed or starting value. Now, please note that I said, and this is going to come up, we will discuss when it makes sense and when it doesn't make sense. But in applications, the starting value does not always make sense. I'm going to go ahead and tie this in a little bit. I was just talking about earlier how some mathematical models only work for a while. Eventually, they fall apart. When they start falling apart, that's when y-intercepts start. Let me rephrase that. When they start falling apart, that's when y-intercepts tend to stop making sense. And again, we will see this in great detail through guided activities, just not today. So y-intercept, starting value or fixed value. So if you go back to those previous problems, we can talk about how some of those things are the y-intercepts. So a y-intercept as a point, so we always talk about x comma y. The y-intercept is always 0 comma something. So that's not a hashtag, that's the number symbol. Your y-intercept is always 0 comma something. Why 0 comma something? Because anywhere along this y-axis, you're not moving left or right, so your x value is 0. This point right here would be 0 comma 12 because you go left or right, 0 and up 12. Up here, maybe this is a height of 20, that would be 0 comma 20. Maybe down here, this is a height of negative 5 million, that would be 0 comma negative 5 million. We are not going to study intercepts as extensively as we would in a traditional algebra class. We're more worried about intercepts being the starting or fixed values, but we still do have to understand the basic traditional sense as well. So what I'd like to do is, and this last line just relates to what we just said, y-intercepts can be found by setting x equals 0. And when I say x, I just mean your input variable. If you're using letters like m for minutes, then you let m be 0. If you're using the letter like t for time, that's your input, then you let t be 0. So the initial time, or talking no minutes, gives you your fixed amount. So if I had, let's say I gave you a graph. And on this graph, we had this point right here, which will be 1, 6. And then we have this point over here. Let's have that be a 10 on the x-axis. And let's have this be an 8 on the y-axis. So I can say these 2 points form a line. Now, if we're doing an application, that's bad. If we're doing an application, we usually don't go, geez, I can't make a straight line. I can't talk and do that at the same time, clearly. If we're doing an application, this is usually how we make our lines. Because in applications, it usually, or quite often, doesn't make sense to go into negative x values. Like we can't talk a negative number of minutes. We can't drive for a negative number of hours. We can't buy a negative number of tickets. So again, in applications, this is usually how we make our lines. But if we're talking about just a pure math problem, no real application to it, then we do tend to extend that line in both directions. All right, so I have established here that this point right here is 1, 6, because we go right 1 and up 6. This point right here is 10, 8. Now, if you need to label these as x1s and y1s and x2s and y2s, remember the first spot is always an x value. The second spot is always a y value. And then you can decide which one are the 1s and 2s as long as you're consistent. I can't make what I'm about to do is wrong. I can't do this. I can't call that a 1 and that a 2. I have to be consistent. If I call the x1, the y is y1, which would force this to be x2 and y2. But I am completely free to swap the 1s and the 2s here. I can call the first point the old and the second one the new. Usually we go from left to right, but it wouldn't get you an incorrect slope because the math would fix everything. So then you can just go m equals y2 minus y1, the difference of the y's, 8 minus 6, over the difference of the x's, again, be consistent in order, 10 minus 1. 8 minus 6 is 2, 10 minus 1 is 9, and that slope is 2/9. What that says is, if you have one point, let's pretend I don't have this point for just a second. I don't have that point. But having this point 1, 6 and the slope of 2/9, the 2 is the rise and the 9 is the run. The run tells you how far right to go. The rise tells you how far up or down to go. Up if positive, down if negative. So we go right 9 from 1 to 10. So that's me going right 9. And then we go up 2 from 6 to 8. And we get our point. Ignore the fact that I drew that just a little off because I was hiding it. But that was going up 2. Up 2. Right 9 up 2. And then from 10, 8, I could go right 9 and up 2. I can go right 9 and up 2. That's the idea of proportionality, but not actually being proportional. We're not saying as one doubles, the other doubles, but we are saying as one has a consistent change, the other has a consistent change. So that's why they're kind of cousins, if you will. Now, we've said several times already that if this line went through the origin, if for some reason you have a line that does start here where the axes cross, this would be proportional, but that's not what we had this time. And it's usually not what we have, in all honesty. It's pretty rare. There's usually a fixed cost somewhere. All right. slope-intercept form, which you've already seen and you just didn't know it. Y equals mx plus b. This slope-intercept form is the exact same as a standard linear model. This is still a standard linear model. This mx right here, that is your variable amount. And the b here is your fixed amount. It's just variable amount plus fixed amount. It's literally nothing different from the last section. But the letters are a little more specific. They're a little more traditional for an algebra concept. Do you have to use these exact letters? No. You can use C equals and blah, blah, blah with an M instead of an X. The M and the B will end up being numbers though. That's the point here. The M and the B should be numbers that you can either find or are given. So like y equals 0.05 x plus 20. That would be the same thing as C equals 0.05 m plus 20. That was the equation we had in the last section for cost equals 5 cents a minute plus the $20 in a fixed flat fee. Slope-intercept form is very, 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 very awesome because the B, the fixed amount, is always right here. This point is whatever the B is. It's always on the y-axis. We call a y-intercept that because it's intercepting or intersecting the y-axis. Those two words are synonymous for a reason. Intercept, intersect. So wherever your line crosses your y-axis, that is whatever this number is. Then the M just tells you how far right and up to go or how far right and down to go to get a second point. So you don't have to plug in a bunch of different x values to get this point and then this point. You can just plot your fixed amount as that height of b. Then you can use the slope and run and rise, or run and fall, is like some people like to say if it's negative, and you can get your next point. It's pretty simple with practice. And then just at the end of the day, one last thing to say before we move on to the guided activity. Actually, I take that back. We're not going to do the guided activity yet. We're going to do a couple more examples. Is that if you know the slope of a line in any coordinate, you can plug these three numbers in and find b, which would be the y-intercept, and then you've got your model completely. What I'm saying is if I tell you a point and a slope, you can plug them into this right here, figure out what b is, and then you've got your model forever and ever and ever. Now, some people might say, well, Mr. Beckner, don't you need the y minus y1 equals m times x minus x1? Sure, you can do it that way. If this was a traditional algebra class, that's the way to do it. If you still remember that way, you can do it that way, but I'm not teaching it that way because it's not really a quantitative reasoning way of doing things. We're just trying to stick to one idea, this variable amount plus fixed amount, and take that one idea and use it in as many ways as possible, just like we were doing with proportions, just like we were doing with other things in chapter 3 and 4. All right, so, oh, I don't have the example type. That's what threw me off, but I know what it is. Line, why am I folded? Line goes through the point, 1 comma 12, a slope of 4. Find the equation of the line. This example right here relates to what I just talked about here. The slope-intercept form, along with, if you know a point and a slope, you can find everything else. Now, points always go x comma y. This is an x and a y. Now, you can label them little ones if you want to, but you don't really have to because they told us the slope is 4. Now, if we were doing that more algebra way of y minus y1, blah, 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 I would label them with ones, but I'm teaching this the QR way. And again, if you know the more traditional algebra way and it works for you, use it. The slope is 4. we said that for some reason, some mathematician decided that the slope should be the letter M. I know that the word slope does not start with the letter M. Maybe the Greek word for slope does. I'm not actually positive on that. But we just use slope being the letter M. Just accept it. Now, what this also means is I could say, all right, when x is 1, y is 12. That's one thing I could say. And then I could say that, if x and y had some concept like x is a number of tickets and y is a cost, then I could say that every ticket costs $4, or tickets are $4 per ticket. That would tell me the slope. Even though I didn't use the word slope, it tells me the slope because it's a per, and per is slope. Anything that's per is your variable amount, and your variable amount is slope. They're all one and the same. So all we're going to do is plug these three numbers into this where it looks like they would go. So instead of y equals mx plus b, the y is the 12 equals, the m is the 4 times, the x is the 1 plus, the b is the, well, what's the b? Well, I didn't tell you that, did I? Leave it that way. Honestly, if you don't want to use the letter B, don't use the letter B. If you want to use the letter F for fixed amount, hey, that would be cool. I'm perfectly fine with that. But what we got to do here is solve for B. Well, 4 times 1 is 4, so that's 12 equals 4 plus B. I really hope you know how to do your algebra to solve this. I'm kind of scared if you don't. Subtracting 4 on both sides, 12 minus 4 is 8. So we get 8 equals B. This is not done. Some people will just box this up and ship this out, and then they get a big fat error, X, whatever. It is true that 8 is B, but it's not the answer. They said to write the equation of the line. We need to write something like this, but with numbers in place of the M and B, and we leave the Y and the X alone. You might be saying, well, Mr. Beckner, why don't you leave the X as a 1 and the Y as a 12? Why don't you do this? Some student would think this is the answer. 12 equals 4 times 1 plus 8. Some people would think this is the answer. Okay, sure, 4 plus 8 is 12. That's true, but this is not a model. This is not a model. This is not an equation. There's no variables in here. This doesn't show you any type of relationship between two things. So that's not what you're supposed to do. What you're supposed to do is let the Y and the X, or the C and the M, or the D and the T, whatever letters you're using, let them be them so they're allowed to change. So we go Y equals 4x plus 8. This is the answer. And you can see that you have your variable amount, that's your 4 per, and here's your fixed amount, the amount that you pay no matter what if this was a cost. If these were costs, I would want to write somewhere that y is cost and x is some number of units, number of tickets, number of something. When I ask for an equation of a line, this is what I'm talking about. Y equals 4x plus 8, y equals 3x minus 7, y equals 1/2 x plus a million, y equals 20x if there is no fixed amount. Some equations of the lines don't have fixed amounts. They usually do, but not all do. So again, I don't have to give everything this way. This problem would relate to, hey, you've got a fixed amount of $8, that's your fee to get in, and you're paying $4 per ticket. That would literally be the same exact model. But this wasn't phrased exactly the same way. They didn't give us the initial amount. They gave us some random amount. This is not an initial amount. This is saying when there's one ticket bought, it costs you $12. But the cool thing is, you can create an equation that ends up giving you the initial amount out of that. That is extremely handy. Because now what we can do is we can graph this quite simply. All I'm going to do is use the information in the blue here. I'm going to ignore the point of 1, 12. In fact, if I do things right, I'll end up picking it up coincidentally. All right. X, Y. So this 8, this is the Y intercept or the initial amount, or the fixed amount, which says on the y-axis there's an 8 somewhere. Let's make it about here. There's our first point. If you don't trust that, if you plugged in x equals 0, 4 times 0 is 0, 0 plus 8 is 8. So when x equals 0, you're going left or right, nothing. You go up 8. Now from that point, what you can do is you can use the slope to find another one. Sure, yes, they did give us 1 comma 12, so you could write 1 up 12 and then connect them. That is absolutely fine. But let's say maybe they didn't give us this information. Maybe they didn't give us this information. They told us the initial amount and the variable amount, and we got to graph the line with that method. Now, you certainly could plug in any other x number you like, 2, 3, 5, and see what the y value is, make a point and plot it. But what we can do is, with a slope being 4, well, that's not actually good enough because we need to see the rise and the run. This feels weird, but when we want to plot a second point using the slope, we actually want to write it as a fraction if it's not 1. Because that way we can see that the run is 1. So that says we're going to go right 1 from any initial point, and the rise is 4. Because it's positive, we'll go up. So from this point, we're going to go right 1 and up 4. Now, if I go right 1, we started at x equals 0, so we end up at 1. If I started at 8 and we go up 4, 9, 10, 11, 12. Sorry, they're not spaced perfectly. I'm not going to correct that. And there's our second point, and then you can connect the lines and extend. Let's assume that this is a model, so negative x's don't matter. And there we go. And again, look at this. That point that we picked up was just coincidentally 1 comma 12. So you're thinking, well, Mr. Beckner, I shouldn't do it that way because it's more work. Again, maybe you weren't given the 1 comma 12. Well, Mr. Beckner, couldn't I just plug in whatever x number I like and find whatever y value it corresponds to? Sure. If you plugged in 1, 4 times 1 is 4, 4 plus 8 is 12. Boom, there you go. Or you could plug in 2. 2 times 4 is 8, 8 plus 8 is 16. So that point would be 2 comma 16. And guess what? From this point 1 comma 12, if you went right 1 and up 4, you would end up at 216. If you plugged in x equals 3, you'll get 20. If you go right 1 and up 4 from 2 comma 16, you'll end up at 3 comma 20. Then 4 24, 5 28, 6 32, 7 36. That pattern will continue. And you can keep railing through them a lot quicker with that pattern established. All right, before we get to the guided activity, ignore this for a second, much longer than a second, in fact. Let's make sure we understand the difference of positive and negative slopes as well as zero slopes. So let's just put the 3 basic scenarios. We don't get into vertical lines in here, thankfully, which would be an undefined slope, FYI. Let's have a line that looks like this. Sorry about the squirreliness of it. A line that looks like this, and then a line that looks like this. This first example, as we go right, we go up. So that's a literal rise, which means your slope is positive. So m is greater than 0, that says your slope is positive. Here, all we ever do is just go right. We never go up or down. If we don't go up or down, that means that the rise is 0, and 0 divided by anything is, that's right, 0. Horizontal lines have a slope of 0. That's perfectly fine to see. So in fact, your equation would just be a number. It would be like y equals 5, y equals 7, y equals 40. Because if the m is 0, going back to this wouldn't be here at all, and you just get y equals your starting amount. So this is like you just pay $20 for your cell phone plan, and you're not paying 5 cents per minute. There is no variable amount. You just pay the $20 flat fee. So that graph would actually be a horizontal line with a height of 20. It wouldn't matter how many minutes you talk if you're only paying the flat fee. And finally, this one, as we go right, remember we're always moving right, this one goes down instead, which says that this is a negative slope. I'm just doing it in a different color to establish that point. No particular reason besides that. All right. What time we got? About 20 minutes. I think that will be enough. Okay. Da, 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 da. All right. Can I highlight on this screen? It's not really a highlight that's covering it. Pretend I highlighted this. Just pretend I highlighted that. This is going to be used in several of the guided activities. This is used at least once in the homework. And I could throw it on the final. I don't think that I usually do. Like I said, I try to be honest about what's on something. But this right here is an important concept. This is something that you can use in the real world all the time. Just like when we were talking about that cell phone plan, but we can be very methodical with our phrasing. Now, these little sideways arrows that look like less thans and greater thans, these are just saying you put a word in its place, whatever is relevant, or a number, whatever is relevant. So the output is changing by, so the output is the thing that the Y is. So when we were talking about our cell phone plan, the output was the cost. That's what the Y related to. So output, again, that's kind of like what the Y is if you're using traditional X's and Y's. Then you use the phrase is changing by. You could also use words like increasing or decreasing, whichever is relevant, by. Then the slope, that just means you're going to put a number. The Y units per X units. So this right here is just talking about something like miles per hour, or cost per ticket. Remember, the word per is your slope. So this is just saying the number with its appropriate units, because we're not just going to say the slope is 5. We're going to say that this thing that we're talking about is changing by this many units for that many units. So it's changing by 5 cents per minute we talk, or the cost is increasing by $2 per ticket we buy. This right here is what we call a cookie cutter. It is an exact phrase that you're going to use, but you have to practice with it. I know I am a broken record. Practice makes perfect. The wording seems very weird at first, but after you do a dozen of them, it's not so bad. Don't worry about this notation. We really don't see this anywhere else in the course. This is called a delta. It just represents change, as they indicate here. So again, this sentence right here is relating to that cell phone plan earlier. The cost is changing, or we could have said the cost is increasing by 5 cents per minute, or $0.05 per minute. Because every extra minute we talked, we paid 5 more cents. Okay, so let's try it out. Oops. Back on annotate, clear, off, scroll. Okay. This worksheet asks you to interpret slopes as rates of change using the sentence template as we already described previously. So the output, the Y, whatever that is changing by, or is increasing by, or is decreasing by. Write the number for the slope, then the ratio of those two units. But it has to be the output to the input units. So here's the graph of our monthly cell phone plan bill, whatever phrase you want to say for that, which we have seen before. It stops at 300 minutes. It doesn't go to 400 minutes, but that's perfectly fine. And this includes the variable amount, and it includes the fixed amount. So we can see our fixed amount here. When we don't talk at all, we pay $20. And then the run and the rise demonstrates the slope of 0.05. So every time you go right 1, you're going to go up 0.05. But this is me actually showing right 100 and up 5, which is the same ratio if you were to reduce it. But that's not what we're supposed to be describing here. We've already done all that stuff. We're trying to interpret the slope of the equation in real world terms using this cookie cutter template. So we say all right, the output. What exactly is the output? You might say dollars. The output's dollars because that's what Y is measured in. Well, Y is measured in dollars, but that's not the output. That's how it's measured. The output is the cost. Now, some might say cost, some might say total cost. I like total cost because that really implies it accounts for the variable and fixed amount. So the total cost is changing by, that's the next part of the template. Or if you didn't want to say it's changing by, you could say, well, it's increasing, so it's increasing by. Then the next thing is the slope, the value of the slope, which is the number paired with the variable. That's the variable amount, 0.05. And then you just write the apples per orange, miles per hour, whatever that is. So what are we talking about? We're talking about dollars per minute. Dollars is the Y output, minutes is the X input. So we're going to say by 0.05 dollars per minute. If you prefer, if you wanted to talk in cents, then you could say we're increasing by 5 cents per minute. 5% would not be a great way of saying this because of the 20. So we can't really say that we're increasing by 5%. The fact that cents relates to 100 makes it feel like you could, but we do need to strictly use those units. So that's a good idea, but it's not exactly the same. Now, if there was no fixed amount, we could say 5%, but again, the point of this activity is to use the specific units they give you. So it wouldn't work for those two reasons. It's a good idea, but it's not perfect execution. All right, so there's our cookie cutter template. The total cost is increasing by 5 cents per minute or $0.05 per minute. If you wanted to do this in hours, you'd have to convert these numbers to hours by using dimensional analysis. It wouldn't be the end of the world, but it would be more time, and we're trying to avoid that. All right, so in the 6 or 7 minutes we have left, let's try and knock out these other two. Now, what I could have done is I could have given you that sentence and then asked you, and as well as the fixed amount, and then you could come up with the equation, you could graph it. You can go either way. I can give you the equation and the graph and ask for the sentence, or I can give you this sentence. I also have to tell you the fixed amount, and then you can build the equation and the graph. All right, let me see if I can get both of these on the screen at the same time. Okay, good enough. So the concentration of pollutants. So this is basically saying at time 0 days, there's a spill in some lake or river somewhere, whatever. And over time, the pollutant dissipates into the air, the water. So this is showing that it's dissipating, it's going down over time. So this 100 would be the initial amount of the pollutant, and this minus 0.8, that's how much we're losing per day since we're measuring in days. So when we go to make our sentence, we can say that the output, which is the pollution, we could say the pollution, we could say the concentration of pollution, or we could just say the concentration, since, well, it did actually say pollutants. I know I'm hiding that word on my screen, but it does say pollutants. So the concentration or the concentration of pollutants, pollutions, however you wanted to phrase it, is changing by, or since it's negative, we can be more specific and say is decreasing by. Now, since I used the word decreasing, if I said changing, I would use the negative, but decreasing implies negative, so I'm not going to write the negative. I'm just going to write 0.8. And then we write the ratio of the different units. The different units are the parts per million and the days, and it goes the Y value over the X value. It's not changing by 0.8 days per parts per million. It's changing by 0.8 parts per million per day. It's kind of weird because the Y unit part per million has a per in it. So this Y value is actually a ratio. It's kind of cool. So again, I could say the concentration is decreasing by 0.8 parts per million per day, or I could say it's changing by negative 0.8 parts per million per day. Those would both be acceptable. All right, this last one is measuring the Houston metropolitan population. Now this 5E.06, that's something in scientific notation, which we have mentioned very, very lightly, and I mentioned that it's something you're supposed to study on your own. If you're in my MDE class, we did go over that because it's developmental or prereq material, however you want to call that. But that just means you take the 5 and you move its decimal right 1, 2, 3, 4, 5, 6 times. So there'd be 6 zeros, so that's Y equals that number with the X plus 5 million. That's what that represents. If that's a negative, that means the decimal goes left 6 instead. Now we don't even need that number for this problem. All we're doing is interpreting the slope. This is the intercept, or the fixed amount. So it has nothing to do with question, thankfully. But we will talk about it later. So the slope. We're talking about the growth of population. We're talking about the growth of the people, specifically for Houston. So the Houston metro population is changing by, or because it's going up, is increasing by. And then we write the slope, which is that 123,139. And then we do the ratio of the two different units. Well, we're talking about people and we're talking about years. Now, that doesn't just say years, it says years since 2000. That is going to be a very important distinction as we move forward. And I just realized I thought I had 7 minutes. I looked at my clock incorrectly. I am not that rushed for time. So, do we do years per people? Does that sound right? The population is increasing by years per people? No, that's not right. Writing the units in that order does not make sense. It's not for every one person increase, there's another 123,000 years. No, it's for every 1 year that goes by, there's that many more people. So it's people per year, question mark? Now, I've already pointed out that the fact that that thing says years since 2000, this is what ties together that whole mathematical models fall apart eventually side of things. This is how we prevent them falling apart for a while, at least, relative to where we are. If this just said that the Houston metro population is increasing by 120,000 people without the per year, that would not make sense when you look at the grand scheme of things. Because if you go back to, say, the year negative 3000 AD or 3000 BC, Houston didn't even exist. So from the year 3000 BC to the year 2999 BC, because they go down, did the population increase by 123,000 people? No, that's a horrible model. But if we only talk about things since the year 2000, since Houston has been established as a metro and is growing at a pretty consistent rate, then it can make sense. So just saying people per year, things get a little sketchy. But by saying people per year since some year close to us, that's how we can make population dynamics work a little better, whether we're talking about population growth, whether we're talking about dispersion of a virus amongst the population. We can have more accurate details when we look at a smaller time frame. That's how we make models actually work, by looking at a small time frame instead of a large time frame. Now, the idea of small and large depends on the type of model. Right now, we're dealing with linear models. We're going to graduate to exponential models eventually, and exponential models can look at a longer time frame. This model for the Houston population is probably going to fall apart in the next 10 years or so, this one that we're looking at. By 2030, it's probably going to slow down, or maybe it'll take off, but it's probably not going to stay consistent because people are dynamic. We change based on laws, based on things going on around us, whatever. So that's one of my favorite concepts, is how when we look at short time frames, one model is good. When we look at kind of medium time frames, another model that's a little more complicated is better. And then when we look at super long time frames, we're going to need a much, much, much more complicated model to deal with population dynamics. Now, when we're talking about a cost of something, models typically don't really change. When we talk about driving, if we're not accounting for pit stops and traffic, that model is not going to change. When we talk about people, something inherently is going to change at some point. Show me 2,000 years of history in which nothing changed. Since we have become, what's the phrase I want to use? Indoor dwellers, I guess. All right, one more. And this one gets a little weirder. And we'll probably end up finishing it here today. Just looking at something else. Interpret the slope of the equation in real world terms. Same thing as before. We have our equation, which gives us the slope and the y-intercept, although I'm not talking about the y-intercept yet. Notice I said yet. We've got nice things labeled, dollars, monthly balance, and whoa, that's weird. Both the y-axis and the x-axis are talking about dollars, but they're talking about dollars of different things. One of them is dollars of a monthly balance in a savings account, and the other is the dollar amount of interest. So this isn't well labeled. It does say monthly interest here, so that's implied, but I would prefer that somewhere this says interest along that y-axis. And again, it is labeled here, so that's good enough, but if you want to be thorough, I'd label it here too. Now, this equation looks a little different than the other ones we just had, because this line isn't going all the way to the y-axis. It's not doing that. Also, I need to be clear that this right here, this line right here, this is not the y-axis in a traditional sense. It is the labeling of the y values, but it is not the traditional y-axis. And that's because this value right here is not 0. It's 16,200. So this graph is actually a zoomed in version of another graph. And what that graph would look like .
And I'm just going to be skipping a little bit because I did a pretty bad job drawing the graph my first attempt. And we're running short on time, so you're about to see all that erase, and here we go.
Sorry. I'm trying to work with the space I've got. Let's call that 82. Let's call that 89. That'll be much better. Then here's our 16,200. Here's our 18,000. Sorry, it's getting a little ugly. This is a much better depiction if you want this to be 0 and 0 on the x and y axis respectively. That's what I mean by this picture right here is really a zoomed in picture of this model, this graph below, because this one does not have 0 labeled on the y-axis. This does not have 0 labeled on the x-axis. So these are not traditional x and y axes, which means if you trace this thing back to here and tried to call that the fixed amount, it's not the fixed amount, in fact, because it's not on the y-axis. You would have to take this one down here and trace this all the way back to the y-axis, and this is not drawn appropriately, but if I did draw it appropriately, it would end up going to here. And that would actually make sense because interest is a product of your balance and time. Interest is just a product of your balance and time. Sorry, balance and rate. Time as well, but it's got all of them. Interest is PRT, principal times rate times time. The time aspect we will use sometimes we don't. We typically will not in here for reasons we'll explain in the next chapter. But interest is just a product of your balance times your APR, your periodic rate, whichever it is. That was stuff we talked about back in chapter 1. That stuff you're supposed to have memorized by now. Yes, if you're talking simple interest over several years, you can throw in that time part, but our models don't use simple interest moving forward. So if you have a balance of $0, you should have an interest of $0 because $0 times whatever your savings rate is should be $0. So that's why if you actually look at the whole picture, it starts to make sense. Whereas here, it kind of looks like you'd think that's 0, 0, but it's not. It's like 16,200 gets you 81 bucks. All right, but the whole point of this was to write our equation, and we got to do that right now. I just wanted to make sure you understood you sometimes are given graphs that are not necessarily starting at an origin. The media loves to do this. It loves to try and confuse people because they can say, oh, well, this looks really bad. Well, I mean, it's not even the whole picture. You got to look at the whole picture to get a full understanding of it. So let me just rock my sentence right here. And we would say that the monthly interest is increasing, changing by sorry, something happened. The monthly interest is increasing by, now you use the slope, which is the number in front of the x, and I don't know why I'm pointing with my finger because I don't have the pen in my hand, 0.005, so by 0.005. Now that's measured in dollars. Interest is measured in dollars, so it's increasing by $0.005 per. Now you might say, well, the unit in the x value was dollars. But that just seems weird. It's increasing by $0.005 per dollar, whether you have the S or not. Well, you need to be a little more specific since these are both the same type of unit. Your interest is increasing by dollars based on a number of dollars of monthly balance. That's more well said. It's better said. The interest is increasing by $0.05 per dollar of monthly balance in the account. So $10 would get you 5 cents. $100 would give you 50 cents. $1,000 would get you $5. That's what this model goes to. We'll talk about this 2e to the minus 11 next time. We have essentially finished this section, so I am going to say that 5.2 is still due on the due date we had up originally at the beginning.
Which you can very clearly see here. Like I said, 5.1 and 5.2 we're going to be due in a week. Everything else we've talked about 30 or 40 times, I feel like, so not going to repeat, but you can see those dates for the last 30 seconds of class. Mainly just want to reemphasize again that the 2 days of availability for your midterm that will be in my math lab at the very top of the assignments are the 12th and 13th, Monday and Tuesday. So coming up, so 6 and 7 days from now, respectively. Hopefully we don't have to talk about that any further. I will give you one more reminder probably next class, but besides that, we'll keep moving forward. We'll push forward through chapter 5. We'll be in chapter 6 in no time, and then chapter 8 and 9, we only have a couple of weeks left, so we're going to just keep on cruising along. So please, please, please keep working on your homework. Most of y'all are doing a great job with that. Keep working on your quizzes. If you have to shoot me any emails for feedback on that quiz, just let me know. Or, well, obviously shoot the email. And besides that, have a good day. Crunch that homework, start studying, work on that review. Again, the review is not mandatory, but I highly, highly, highly recommend that you do it because it will let you know what to focus on for the midterm. All right. So yeah, email me if you have any questions. Besides that, take care, and we'll see you on Thursday.